Hello, I'm Keke. Welcome to our fourth lesson in this series on gravity and mechanical energy. In this series so far, we have investigated how things fall and showed that there is a difference between mass and weight. In our last lesson, we found out what work really is and showed that when work is done, energy is transferred. This energy can take the form of potential energy or kinetic energy. The sum of potential energy and kinetic energy is called mechanical energy. Now, in this lesson, we are going to focus on the relationship between work and weight. So by the end of this lesson, you should be able to explain how work and weight are related and calculate the energy transferred when an object is lifted from the Earth's surface. Now, to begin, let's look at the task I gave you at the end of the last lesson. Calculate the work done by the gravitational field when a ball with a mass of 250 grams falls from a height of 15 meters above the ground. The first thing we need to do is find the weight of the ball. Remember, weight can be found using the equation W equals m mass times g gravitational acceleration. I substituted the mass in kilograms and the gravitational acceleration. I found that the weight of the ball is 2,5 Newton downwards. The ball fell from a height of 15 meters, so its displacement is 15 meters. Now I need to calculate the work done by the gravitational field. Can you see that the force and displacement are in the same direction? So I can calculate work done by the gravitational field. The equation for work done is written as W equals F times S. Even though weight and work have the same symbol, W, they are not the same. Don't get these two W's mixed up. The force applied to the ball is its weight, and the displacement is the height the ball fell from. So, I can substitute in the values and find the work done by the gravitational field was 37,5 joules. In this case, the gravitational field did the work and caused the ball to accelerate downwards. Now remember, whenever work is done, there is a transfer of energy. Do you know what type of energy the ball has gained? Yes, the ball has gained kinetic energy. Did you know the English word kinetic comes from a Greek word that means move? The word cinema comes from the same Greek word because you watch moving pictures in a cinema. In this example, the gravitational field did work on the ball and transferred kinetic energy to the ball when the ball fell downwards. But what happens when we lift objects? Is work being done and is energy being transferred? Let's get Aaron to investigate.
Hello guys, look here. I've got the same apparatus I used when I was dragging the mass pieces across the table. But now in this experiment, we're going to lift them up straight using the spring balance to measure the force applied when we lift them up. And our displacement is going to be 1 meter, hence we've got the meter rule. Okay, let's pull up the first mass piece at a constant speed. And it gives a reading of 1.5 newtons. Remember, it's always important to have your readings. The displacement, 1 meter, constant. Now remember that our spring balance measures the weight, which acts downwards. So in order to lift an object upwards, you need to apply a force equal to the weight. Okay? Now we've got our readings for the first mass piece. Let's go for the second one and see what happens. Gonna attach the next mass piece, which has a greater mass. So now, to lift a mass piece with a greater mass, we need to apply a greater force. Let's see what happens. And it gives us 3 newtons. 3.0 newtons. The displacement, 1 meter. Now, do you think I've done any work on these mass pieces? by lifting them up. Let's go back to the studio to check your answers.
Thanks, Aaron. Well, I hope you were able to see that Aaron did do work on both the blocks. He applied a force that caused the blocks to be displaced by 1 meter upwards. In fact, we can calculate the work he did. Do you remember what equation to use? For the first block, he applied a force of 1,5 Newton. This is the weight of the block 2. He lifted the block to a height of 1 meter above the table, so the work done is equal to 1,5 joule. By substituting in the values of the heavier second block, I can calculate the work done to be 3 joules. What conclusions can we make from these two experiments? Well, firstly, when we lift things up, we are doing work against the gravitational field because a force is applied and there's a displacement in the upward direction. Secondly, the force we apply is equal to the weight of the object. The direction of weight and the force are opposite, but they have the same magnitude. Also, notice that when the block had a greater weight, a greater upward force was required to lift it. So when the weight is greater, more work needs to be done. But are there any other factors to consider when doing work against gravity? I want you to watch this weightlifter carefully. When does he do more work? When he pushes his 60 kilogram mass to a height of 20 centimeters or to a height of 50 centimeters? I'm sure you will all agree more work was done when the displacement was greater. But what about this situation? The man is holding this large weight above his head. Is he doing any work? He is clearly applying a force upwards, but the weight is not changing position. So even though the man is making an effort, he's not doing any work really. So, can you see work is not only dependent on weight, but on displacement too. When there is no change in position, no work is done, even if a very large force is exerted. Now, another important thing to remember is the direction of the force and the displacement. But the direction of the force and the direction of displacement must be the same. When a weight is lifted 1 meter above the ground but takes a diagonal route which is 4 meters long, no extra work is done against gravity. The upward force and the height must be in the same direction, vertically upwards. So when lifting objects up against the gravitational field, we can calculate the work done by multiplying the upward force by the vertical height lifted. But remember, the size of the upward force is equal to the weight. So we can simplify this equation some more. We know the weight, W, is equal to the mass, M, times the gravitational acceleration, G. We can use the symbol H for vertical height, and this gives us an equation, W equals mgh. Now there's one more question we need to answer. We need to know that whenever work is done, energy is transferred to the object. When the go-kart was pushed, work was done and kinetic energy was transferred. When the ball fell, the gravitational field did work on the ball and transferred kinetic energy to the ball. So now when objects are lifted, we know work is done. But what energy transfers have taken place? Well, while Aaron was lifting the blocks, they did have some kinetic energy. But once he reached the height of 1 meter, the blocks did not carry on moving. If he were to release the blocks, the gravitational field would cause it to fall. So because of its position, it has energy. We say it has gravitational potential energy. The work done in lifting any object against gravitational field is equal to the gravitational potential energy. We use the symbols E subscript P for gravitational potential energy. Can you think how we could calculate this gravitational potential energy? Remember, the work done against the gravitational field is mgh, and this is equal to the gravitational potential energy. Let's look at some everyday situations where things gain gravitational potential energy. Here are learners walking upstairs. Are they doing any work? Did you know that there is a reward for this hard work? Their gravitational potential energy increases as their height increases while they climb higher and higher. And what does an increase in gravitational potential energy affect? When your gravitational potential energy increases, you have stored gravitational potential energy in your system, and you can release this energy to perform some useful functions. A diver releases his stored gravitational potential energy when he falls. The gravitational potential energy is converted into kinetic energy. When he hits the water, the kinetic energy is transferred to the water as it is pushed apart and acts as brake to slow down his motion. Now I want to look at one final situation. Here is a painter climbing a ladder. Let's calculate the amount of gravitational potential energy of the painter when he reaches the top of the ladder. Firstly, we must analyze the situation to find out what force he is exerting as he climbs the ladder. He is lifting his weight and the paint tin against gravity. So he's exerting a force equal in magnitude to his weight plus the weight of the tin can as he climbs up a steady speed. The ladder is 2 meters long, but when he stops climbing, his feet are only 1,5 meters above the ground. Which displacement should we use? 2 meters or 1,5 meters? Remember, the force and displacement must be in the same direction. We know that the force he applies against gravity is upward, so we must use the vertical displacement or height of 1,5 meters. Now, what other information do we need? We need to calculate the upward force. To do this, we need the weight of the tin and the painter. The painter weighs about 65 kilograms. The tin is not too heavy. It weighs about 5 kilograms. But remember, we are interested in the mass of the painter and the paint he's carrying because we are calculating the amount of work done when he climbs the ladder. So let's make use of the information we gathered to find his gain in gravitational potential energy. We will use the equation EP equals mgh. The total mass of the painter and the tin is 70 kilograms. The acceleration due to gravity on Earth is g. We are going to use the value of 10 meters per second squared. The vertical height is 1,5 meters. We substitute these values into the equation and find that the gravitational potential energy gained is equal to 1,050 joule. Remember, this gain in gravitational potential energy is equal to the work done by the painter. Now, unfortunately, just before he climbs down the ladder, the paint tin falls from the top step. The weight of the tin is now 32 Newton, and the top step of the ladder is 1,8 meters above the ground. For your task today, calculate the gravitational potential energy of the paint tin. Also, identify what happens to the gravitational potential energy of the tin. Do join me for our next lesson when we explore the relationship between work and mechanical energy in more detail. Goodbye.